Hello students. So today we will be talking about impurity states. Okay. Now, why this impurity states is important, because often when we are forming a nanocomposite, we are replacing some of the atomic sites by an different atom, which is often called an impurity. Impurity states are also found in alloys, whether it can be an interstitial impurity or a substitutional impurity. But what we will discuss today is the physics behind the impurity states, rather the change in the band structure that occurs on introducing an impurity state. Now we will start with an example. We will assume that there is a group 5 element is being replaced by a group 6 impurity. Now, example, if we are introducing elements like selenium and tellurium in group 5 element. Okay. Now, what will happen to the band structure? Now, the band near k is equal to 0. Now, this k is equal to 0 stands for the minima, okay, or where actually the transition between the conduction band minima and the valence band maxima takes place. This region is often denoted as k is equal to 0, where k stands for the wave vector. Now, what will happen to this point? Now, if we draw the band diagram, this happens to be the band diagram, and this is the conduction band, and below this we can draw, this is the valence band EV. Okay, and this region is called the X region, whereas this region is called the gamma region. Both of them are in fact k is equal to 0 region. This is also k is equal to 0, and this is also k is equal to 0. So k is equal to 0 is noted by two regions. One is the gamma, one is the X region. Now, the orbit associated with lowest impurity state composed of conduction band eigenstate near k is equal to 0 is labeled as gamma. So I will write it down as this. So this gamma, this actually is this corresponds to the orbit associated with the lowest impurity state and it composed of conduction band eigenstates near k is equal to 0. This is called the gamma state. Okay. whereas this X state is the orbit associated with zone boundary K0 is leveled by X. So whenever we have got a zone boundary, so we all know what is a Brillouin zone is. So let me this is the band diagram. Okay, this is the Brillouin zone. This is K is equal to 0. Okay. Now, when associated with the zone boundary, when there is a zone boundary, the orbit associated with that is called K0 or X state. I think I have wrongly mentioned one thing. This is not actually K is equal to 0, this is denoted by K0. So this corresponds to the zone boundary region denoted by X. Now coming to the impurity addition, now the group 6 atom, it acts as a positively charged donor impurity. Okay, so let me write this group 6, it will act as a positively charged donor impurity. And it will give rise to the Coulomb potential. Give rise to Coulomb potential. That's the Coulomb potential. And this Coulomb potential is actually reduced by the static dielectric constant of the pure material. So we will having a Coulomb potential, but it will be reduced by the static dielectric constant. So what we have, the potential as VR is equal to minus E square by epsilon 0. So this dielectric constant plays a role, and it plays a role in reducing the Coulomb potential. This Coulomb potential VR. Initially, it would have been minus E square by R. This interaction of this static dielectric constant of the pure material, or material where the impurity is being added, actually cause a reduction. For example, in gallium arsenide, this epsilon 0 value is 11.6. And this is basically typical for all the diamond type semiconductors like selenium, tellurium, and all the 3,5 compounds all have a dielectric constant similar to this value. Now, apart from reduction of the electric charge, apart from the reduction of Coulomb potential, there is also reduction of the effective value of the electric charge. So initially, if the value of charge is E, now this will be changed to E by root epsilon 0. So the dielectric constant also reduces the effective electronic charge. Now, to solve this, the whole idea of impurity, we need to solve the Schrodinger's equation. So that is minus h cos square by 2m del square psi plus V psi is equal to ER. This is your typical Schrodinger's equation. So this V here is the Coulomb potential we are talking about. So VR is equal to minus E squared by R into epsilon 0. Now, as in the solution of the Schrodinger's equation for a hydrogen atom, this potential leads to bound states of electron in Bohr-like orbit around the impurity. So similar sort of things also take place. So as in the case of hydrogen atom, we have different bound states which are corresponded by minus 13.6 by n squared. So similar to this physics, this impurity atom addition also uh, creates some bound states in the energy level. Okay, so if this is an atom 6 element, so there are different bound states. The first one will be the orbit associated with the near zone boundary, near zone boundary state, and so it will be the sex state, for example, and we can have other states also. For example, this corresponds to the gamma state for k is equal to 0. So we can have different bound states. And this is actually the 3,4 compound. So let me put it in this way. So basically there are a lot of 3, 5, 3, 5, 5, 3, 5, 3, 5, 3, 5. So the different 3 and 5 elements are in the lattice in this form. Due to this addition of this impurity state, this 6 element distance, this potential gets changed, which becomes circulated as 6 dash, and that is how we get the different bound states. Okay. So minus h cross square, one thing and by 2m E star sigma square minus E star square by R to psi is equal to E into psi R. So this is the basic solution where this E is basically the effective charge. This potential is actually the effective Coulomb potential, and the solution of it leads to the different bound states that we observed here.